Okay, let's do a few examples where we calculate probabilities of events when we know that all of the outcomes are equally likely. So suppose we roll two six-sided dice and we ask our event that we're interested in is that the dice sum to 7. How would we go about that? So our sample space is going to be pairs. So the first dice is a 1, second dice is 1, first dice is 1, second dice is 2, first one is 1, second dice is 3, all the way up to pairs of 6s. Right, that's the sample space. And the event we're interested in is the dice summing to 7. So how can that event happen? That means we throw a 1 or a 6, a 2 or a 5, a 3 or a 4, 4 or a 3, 5, 2, 6, 1. That's the event we're interested in. So we have to map our event down to a subset of the sample space, remember? And now to calculate probability, we need to calculate the number of outcomes in S. In this case, it's 36, 6 times 6. And we need to calculate the size of event E. So here it's 1, 2, 3, 4, 5, 6. So the probability of event E is 6 over 36, which is 1 over 6. Let's try another example. Suppose we toss a fair coin twice. What's the probability that we get 2 heads? So the sample space here is heads, 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 tails, tails, heads, tails, tails. The event we're interested in is 2 heads. So the sample space has 4 elements in it. The event E just is 1, so the probability of event E is a quarter. So let's try another example. What's the probability that we get a heads, then a tails? So that means our event is heads, then tails. Again, this is going to be a quarter. Let's ask a different one. What's the probability we get 1 head and 1 tail? That means we don't care about the order now, right? So that could be, then the event is we get a head or a tail or a head. Both are fine. So now our event E has 2 elements, and so the probability of E is 2 over 4, which is a half. You can see our counting is starting. Here, these are all simple examples. We can use to enumerate everything. But more generally, it quite quickly gets complicated, and we have to use counting, all the counting product rule and so on that we learned about, and permutations and combinations to calculate the number of elements in these sets so we can calculate the probabilities. So let's give an example. Drawing balls from a bag. So favourite example. So coins, dice, and balls and bags are favourite examples. So suppose we have a bag that has 4 red balls and 3 white balls. We draw 3 balls. So we draw 1 ball out, then a second ball, then a third ball, don't put them back. So what's the probability that we get 1 red ball and 2 white balls? So we could enumerate this, but it's quite messy to do it. It's simpler to use our knowledge of how to count combinations. So the number of ways we can draw 3 balls out of 7 bags is 7 choose 3, which is 35. Not caring about the ordering. So our sample space is 35 when we don't care about the ordering. And our event E, now if we draw a red ball, then there's 4 red balls initially. So it's 4 choose 1 ways that we could choose a red ball. And then the white balls, there's 3 white balls, and we want to choose 2 of those. So it's 3 choose 2 ways we could choose those. And we don't care about the ordering, right? So we can just multiply that up, and that gives us 12. So the probability of 1 red ball and 2 white balls is 12 over 35. Let's try another example. What's the probability at least 2 red balls are drawn? So what's the event there? That means that we drew 2 or 3 red balls, because we were drawing 3 balls, right? And at least 2 were red. So we can count the probability that we drew 2 red balls and the probability that we drew 3 red balls. So there's 4 red balls in total. So probability of number of ways we can choose 3 balls, not caring about the ordering, is 4 choose 3. And here the number of ways we could choose 2 red balls is 4 choose 2, and then 3 choose 1 is the number of ways we can choose the white ball, because the other one has to be white. Add that up and you get 22, so it's 22 over 35. And if we calculate the probability that at least 2 white balls are drawn, we We can do it all the same way, and we'll end up with 13 over 35. So here's an important trick. So if something looks hard to calculate, often calculating, if an event looks hard to calculate, have a look at the event not happening, the opposite of the event, and see if that's hard to calculate. It might be much easier. So we're using this fact, the fact that a probability of an event E is 1 minus probability of its complement. So the complement is the event E does not occur. And it might be that if counting the number of elements in set E, in the event E is hard, maybe counting the complement's easy. And vice versa, of course, right? So here's some examples. Suppose we flip a coin 3 times. What's the probability there's at least one head? At least one head. So toss a coin 3 times. The size of the sample space is 2 to the power 3. So there's 2 outcomes, heads or tails. So it's 2 times 2 times 2 is the number of possible outcomes. That's 8. The probability that no heads. So counting the probability there's at least one heads, we'd have to count, 1 head and 2 tails, 2 heads and 1 tail, 3 heads, and so on. So that's a simpler way. If we have a look at the complement, which probability that there were no heads, the event, there was no heads. Well, that's just a single one, right? That's the event that with 3 tails. And so that's just got one element in it. So the probability of that is 1 over 8. And so the probability of the event we're interested in, which is at least one heads, is 1 minus that. It's 1 over 8. 1 minus 1 over 8. And then in the case when you tossed it 3 times, we could have enumerated it and calculated it. But it's really easy for that to get out of hand. For example, suppose I toss the coin 10 times or 100 times or 1,000 times. You just can't enumerate all the options, all the ways that you could get at least one heads. But the number of ways you can get no heads still is the same, right? It's just going to be, they've got to all be tails. It's just going to be 1 minus 1 over the number of possible outcomes, right? So working in terms of the complement makes this a really easy calculation. And often when you see things like at least, that's a warning. Have a think about the complement there. That's a hint rather than a warning to think about the complement. But you have to have your wits about you. If you try and calculate an event and it looks really hard, just have a go. Always a good strategy is have a look at the complement and see if it's much easier. We can do the same again. Suppose we toss a dice twice. What's the probability the sum is greater than 3? So there's 6 possible outcomes from a dice. We toss it twice, so it's 6 squared is the number of outcomes. That's 36. The event that it's less than or equal to 3 is going to be, we throw a 1 or a 1, a 1, a 2, and a 2, or a 2 and a 1. So the probability is going to be 3. That's of the complement, sorry. So instead of looking at the sum being greater than 3, we look at the complement of that, which is less than or equal to 3. There's only 3 elements in there, so it's 3 over 36. And so the probability of the event that's greater than 3 is 1 minus that. So again, it's a fairly straightforward calculation.